Hi, I'm Takuya Fukuoka from University of Tokyo. I'm here to present pitfalls of on-demand paging on Infiniband. Computing using distributed environment is popular. AI, big data, scientific computation, and other kinds of computations are conducted using multiple machines in data center and supercomputers. In these platforms, each machine is connected with interconnects, and the overall performance is affected not only by the performance of each machine, but also by the performance of interconnects. Examples of high-performance interconnects are InfiniBand, high-speed Ethernet, Intel OmniPath, and so on. Remote direct memory access, RDMA, is one of the technologies of interconnects for low latency and high throughput. RDMA enables us to avoid the buffer copies and bypass the remote CPU. Please look at the figure below. The conventional communication stack is composed of many layers, and you need to copy the contents of buffers between each layer. In the case of the figure, you need to copy from the buffers of the application to the OS, and then to the driver, and then to the NIC. But RDMA enables us to avoid the multiple buffer copies, and in addition to this, you can avoid the interactions with the remote CPU. Because of this kind of bypassing nature of RDMA, you need to register the memory of the communication buffers before issuing communications. This is usually called memory registration. RDMA is a popular technology and is currently introduced in Infiniband, LoC, and IWAP. However, there are problems with memory registration. The memory regions which are being registered cannot be swapped out. This causes two major problems. Firstly, you can use less memory available for the computation without swapping out. To cope with this issue, many researchers have researched the method to use a registered buffer again and again. The typical method is pin down cache, but it takes high programming cost to manage communication buffers. On-demand paging, ODP, is an emerging technology recently introduced to Infiniband by NVIDIA. This technology avoids the need to register memory beforehand. Instead, under ODP, the memory registration is triggered by page faults on NICs only when needed. In this presentation, we call a page fault on NICs just a page fault. In the figure below, if the requester tries to access the memory of the responder and the memory region of the responder has not been registered, a page fault happens on the responder, and memory registration to the buffer is conducted at that time. The previous book reported the overhead of page fault is around several hundred microseconds, and it's acceptable. Here, I'm going to introduce the contributions of this work. First, we reverse engineer the behavior of ODP. Because the ODP has not been researched so much and not enough information is public, we start this work by capturing packets and observing the behavior. Then we find two critical performance pitfalls of ODP. We will show that the stalls of several hundred milliseconds to several seconds appear in simple conditions. As the figure below shows, this is a surprisingly long stall. Basically, the round-trip latency of Infiniband without ODP is around several microseconds. The cost of a page fault is around several hundred seconds, but the latency caused by these pitfalls is around several seconds. We identify the situation and the causes of these pitfalls using microbenchmarks. We also confirm that they can actually appear in two real systems, AlgoDSM and SparkUCX. And if you are interested in the result, please see our paper. This is today's outline. First, I'm going to explain the basics of Infiniband and on-demand paging. In the experiments, I'm going to introduce two performance pitfalls and detailed analysis using microbenchmarks. Finally, I'm going to summarize today's presentation. First, I'm going to introduce the basics of Infiniband. Infiniband is an interconnect with ultra-low latency, mainly used for high-performance computing. This high performance is supported by RDMA. Infiniband has two kinds of communications operations, and the one is two-sided operations, such as send and receive, and the other is one-sided operation, such as read and write. When issuing communication using Infiniband, each operation is posted to a communication resource called the queue pair. And this is a little bit detailed, but important because we will use it later. I would like to ask you to remember the timer queue pair here. Then I'm going to introduce the transport layer of Infiniband. Infiniband supports four kinds of transport protocols, and among them, reliable connection, RC, and unreliable datagram, UD, is famous. If you are familiar with TCP/IP, you might know TCP is reliable and UDP is not. RC is something like TCP and assures the transport of packets. In the case of packet loss, RC supports retransmission as the figure shows. If a request was lost in the middle of a communication, the requester waits for a certain period until the timeout expires, and then it retransmits the request. Next, let's review what on-demand paging is here. On-demand paging, ODP, is an extension to eliminate the need for memory registration beforehand. Instead of registering memory beforehand, the communication buffers are registered only when needed. Under ODP, a trigger of the registration is page false in NIC, and it happens when the remote memory is accessed for the first time. ODP is becoming popular and currently is introduced in some MPI libraries. ODP is basically implemented on the driver and the firmware in NICs. Because ODP has not been researched so far, the details about how ODP works are not so clear. There is previous research that proposed ODP itself, but it explains that the ODP is implemented by making use of retransmission by RC, but we found that the behavior of one-sided operations enabling ODP is especially unclear. So we investigated the behavior of ODP by reverse engineering through observing the packets. The figure shows how the ODP of RDMA read operations works. And it shows that when a page fault happens, the server asks the client to retransmit the request again. Through this in-depth investigation of ODP, we found two performance pitfalls. We named them packet damming and packet flood, respectively. From here, I'm going to introduce the proof of pitfalls using microbenchmarks. This is the experimental environment, and we use two machines connected with Infiniband. One is a server, and the other is a client. We also use the ConnectX4 adapter in the experiment. Finally, we set the smallest value to the timeout to detect an error or packet loss as fast as possible. You might think this configuration is a little bit detailed, but this is an important point and use it later, so please remember this here. This is the overview of the first pitfall called packet damming. This pitfall basically happens when we issue two RDMA read operations at a certain interval. The characteristics of this pitfall is that the packet gets stuck for several hundred milliseconds, and we found that the root causes the packet loss and subsequent super long timeout. By the way, we found it by analyzing another distributed system, and we took several months to identify that the root cause is ODP. This is a microbenchmark used for reproducing packet damming. This is a very simple benchmark, and just one machine issues two read operations to the other machine. We change the interval between two communications. the message size is fixed at 100 bytes, and we use a single queue pair, a communication resource in Infiniband, and we apply ODP to both sides. This is the result of this micro benchmark. The x-axis shows the interval between two communications, and the y-axis shows execution time. When the interval is 500 microseconds to 4,500 microseconds, the execution time is around several hundred milliseconds. This is unexpectedly too long execution time. After our detailed investigation, we found that the packet loss and subsequent timeout happened in this situation. And we found the long execution time comes from the timeout. However, this is a weird phenomenon because we set the timeout to be minimal. To investigate it more deeply, we measure the actual timeout, actual minimum of the timeout. The x-axis shows a parameter that users can set, and the y-axis shows the actual value of the timeout. Interestingly, the red line shows that the timeout cannot be set to be any smaller than 500 milliseconds. This minimal value is pre-configured in the firmware, and users have no means to modify it. The true reason why Infiniband is configured in this way is unclear, but we suspect that this configuration does not affect the performance in the general usage of Infiniband. This anomaly appears only when ODP is enabled. Next, I'm going to introduce a second pitfall, packet flood. Packet flood is a pitfall related to the queue pair, a communication resource in Infiniband, and it occurs only when multiple queue pairs are used. Specifically, it happens when you issue RDMA read operations using several queue pairs with client-side ODP. The characteristics of this pitfall is the occurrence of a huge number of packets by the transmission of packets. We found that this leads to the super long latency of several hundred milliseconds to several 10 seconds. And we also identify that the root cause of this pitfall is the failure of updating page statuses. This is a micro benchmark for packet flood. This is a similar micro benchmark as one for packet damming, but there are several different points. First, the number of RDMA read operations is around 8,000 at this time. Second, there are no intervals between communications operations. Lastly, and most importantly, we use several queue pairs and change the number of queue pairs. This is a result of the micro benchmarks for packet flood. The left figure shows execution time of the micro benchmark on a log scale, and the right figure shows the number of packets. In both figures, the x-axis shows the number of queue pairs. But as the number of queue pairs increases, the execution time increases drastically by several hundred times. At the same time, you can see the number of packets increases as the number of queue pairs increases. This increase in packets is caused by the transmission, and with our detailed analysis, we identify that the root cause is a failure of updating page statuses among queue pairs. I don't explain so much here, so if you are interested, please see our paper. This is a summary of this work. We have found two performance pitfalls of ODP, and in certain situations, the latency of ODP is longer by 3 to 4 orders of magnitude than the overhead of an page fault itself. We have reproduced and analyzed them using simple micro benchmarks. These are take-home messages of this work. The common point of the pitfalls is that they are related to the concurrent page faults, and the current hardware-based implementation of ODP is much more fragile than expected when concurrent page faults are related. Finally, to make the implementation of ODP better, we have reported the pitfalls to the vendors. Also, we think that an approach coordinated with the software could be one choice. So if you are interested, see our paper. That's all of my presentation. Thank you for listening.